there are many features of the nucleus and various nuclei that were noticed but couldn't be explained by a simple model like the Fermi gas model of nucleons. Some of these things are the fact that there are certain magic numbers in nuclei, numbers of neutrons or numbers of protons that were especially tightly bound. They had a lot more binding energy than the neighbors, and other factors also contributed to certain magic numbers, as they're called, of neutrons and protons. And these numbers, as they've become known, the magic numbers are 2, 8, 20, 28, 50, 82, and 126. Some of these we can see in the chart of nucleides that I have here. I've marked the 20 line and the 28 line in both protons here and neutrons here. And you'll notice that the isotopes of calcium have many stable isotopes there. There are 7 stable isotopes, whereas at lower numbers of protons, lower atomic number, none have more than 4 before that. Most have only 2 or 3. And the isotones with 20 and 28 are also especially populated. We can also see, if we point out the doubly magic numbers for 2, which is the helium here, and 8, 8, which is the oxygen here, are especially tightly bound nuclei, so that the magic numbers also show up for helium and 16 oxygen. Oxygen has atomic number of 8. Helium of 2 are really have a lot more binding energy than the neighbors, and so I should have perhaps drawn in lines on this for the magic numbers at 2 and 8 and 2 and 8 as well. And then as you go higher into the numbers of neutrons and protons, we see similar things at 50, which has 6 stable isotones, and tin, with the atomic number of 50, has 9 stable isotopes. 82 has 7 stable isotones, and at 126 we have the especially tightly bound lead-208, which is a doubly magic number with 82 protons and 126 neutrons. So we would like to explain the existence of these magic numbers in a shell model. And so in doing that, we are comparing explicitly to atomic shells, where you might know from the periodic table, we have especially tightly bound atomic shells with 2, 10, 18, 36, 54, and 86 electrons. And if we go a little farther, probably 118 electrons as well. Those atomic numbers are tightly bound atomic shells, and they show up in the periodic table. So let's take a look at the periodic table. I have here the periodic table shown, and as well as the ionization energy for elements. And if an atom is tightly bound, if the electron is most tightly bound to the atom, then the ionization energy is higher. So looking again at the shells, in the first shell, the first row of the periodic table, we have hydrogen and helium. Helium has 2 electrons and is tightly bound. And then we go along the next row, and we go up to neon, with 10 being the next inert, then 18, and then 36 once we get to krypton, 54 for xenon, and 86 for argon. And if we complete out in this version of the of the periodic table, 118 in the last row once it's complete. And if we look at the binding energy of these, we see that helium has a very high ionization energy, which means it takes a lot of energy to get one electron away from the helium atom, and so that the electrons are tightly bound. Same with argon, or sorry, neon, argon, krypton, and argon. So we would like to explain all this. We can explain this, though, from the solutions to the hydrogen atom in quantum mechanics. Now, I'm going to assume that you've all seen the solutions to Schrödinger's equation for the Coulomb potential before, but I thought I would review it here, because we're going to expand on it to look at the nuclear potential. So I'll write out the Schrödinger equation for for a spherically symmetric solution. And this is a time-independent Schrödinger equation. So we have minus h bar squared over 2m, Laplacian of the wave function, plus the potential, which is only a function of r for a spherically symmetric potential, times the wave function equals energy, which is just a number, times the wave function. And solutions to this equation are the allowed states, allowed state wave functions for this. You may recall that this first term has to do with the kinetic energy. The two derivatives give momentum out of the wave function, and we have p squared over 2m, so that's how the kinetic energy appears. This is obviously the potential energy because we put in the potential explicitly, and then we have the energy. In this, since we're assuming spherical symmetry, we should do this in spherical coordinates, and so in those coordinate systems, the Laplacian operator is 1 over r squared d by dr of r squared d by dr plus 1 over r squared sine theta d by d theta of sine theta d theta d by d theta plus 1 over r squared sine squared theta d squared by d phi squared. So we have the radial derivatives arranged like this, the azimuthal, the polar angles derivatives like this, the azimuthal angles here. Note that we're going to, that only the r component appears in the potential. Now, the standard way to go about solving this is to write down the wave function, which is a function of 3 variables, as a product of 3 functions, each of which is only a function of 1 variable. We use separation, we only look for separable solutions. And so we often use capital letters for the function and of the little letter variable. So we have a radial function times a polar function times an azimuthal function. And we assume that only wave functions that have the separable form are the ones that we are going to look at. Now, we can actually, we could treat each separately, but I'm going to skip ahead and just combine the polar and azimuthal parts, the angular parts of the Laplacian, into an angular momentum operator and find solutions to that rather than doing azimuthal and polar separately. So we can define a differential operator, which we're going to call L squared, and we're just going to plug in an extra constant for use later, the minus h bar squared, but then 1 over sine theta d by d theta of sine theta d by d theta plus 1 over sine squared theta d squared by d phi squared. So this has the azimuthal parts here without the r squared, but with an extra h bar squared. Okay, so with that operator, I can find solutions, functions, which solve, for which when I apply that, I get eigenvalue solutions. So I can say what that's in a second here, and I'll write it here on this page. So I want to find functions of theta and phi which are eigenfunctions of this operator. So this is a differential operator. I say that there's these functions which have these funny form YLM of theta and phi. But when I apply that operator, I get back out the same function, but maybe with a constant. In this particular case, the constant is h bar squared L times L plus 1. And so in this case, we say that the YLM functions are eigenfunctions of this operator L squared with the eigenvalues h bar squared L times L plus 1. Remember, the h bar squared was part of the operator as just a number, so it's not surprising it appears as in a constant there. I forgot to introduce, in addition to the L squared operator, we can introduce another differential operator, L sub z, which is minus I h bar d by d theta. Excuse me, d by d phi. And so the YLMs are also eigenvalues, it turns out, eigenfunctions of this operator, so that YLM, when acted on by LZ, produces YLM back, but this time with a constant that depends on M. I see that I miswrote. Here, this should be a phi. So these functions are well known. The YLM functions are the spherical harmonics, well known. And anytime you have a problem in which there is spherical symmetry, solutions of this type will appear because they solve because they are eigenfunctions of these two operators. So, in fact, I have put in examples of what these functions look like in several cases. In each of these cases, you're taking a sphere and sort of unwrapping that sphere into this oblong shape. And then the blue and the red describe when L or when the YLM, particular YLM, is large or small, meaning positive or negative of large amounts. And the captions are a little hard to read, but in this particular case, I believe L is 2 and M is 0, and you get this kind of case where there's no azimuthal dependence at all. That's often the case when M equals 0, and then you get this positive at the poles and negative at the equator. That's as opposed to this one over here on the left, where I believe it's still where I think Y is 2 and L is 2, and you get lots of azimuthal variation because the M is high. By the way, there's a M minus 2 as well. I should say the properties of these of the M's in the YLM, M will always be between L and minus L. So there are 2L plus 1 M's in every L. And so coming back here, we have these are L equals 2, and you have M equals 0, M equals plus or minus 1, and M equals plus or minus 2. And then I believe as we go down through the rows here, this is L equals 3, and this is L equals 4. And then some, but not all, of the M's going along here. So every time we have spherical symmetry, we're going to want to expand the angular part in spherical harmonics. And even if there's not spherical symmetry, we can still, if we treat the problem in spherical coordinates, we can use the spherical harmonics in the solution. So with the spherical harmonics in hand, we can rewrite the wave function solution that we're looking for as psi of NLM. We give it some quantum numbers. We already know what the L and M are going to be, but we're just introducing N at this point, of some R vector is going to be, and I'm going to write it as UNL of R over R, still all that's a function of R, times YLM of theta and phi. So we know the YLMs already and what their properties are, and so if we plug this into the Schrödinger equation and get rid of all the other coordinates and write it as a function of u, we get a new differential equation, which is d squared UNL dr squared minus 2m over h bar squared v of r UNL, also of r, minus L plus 1 over r squared times UNL. All of that equals minus 2m over h bar squared ENL UNL. So recall UNL is a function of just r. Here it is. And it satisfies this differential equation. The fact that we have these L solutions gives rise in the equations to this extra term, which is the centrifugal potential part. As L comes bigger, as L is bigger, you get a larger term here repelling, causing a term which gets bigger with R and repels, pushes away solutions that would be close to R equals 0. And recall that we're looking for values, solutions to this equation which have this constant value energy. Those are the eigen solutions. They'll have a particular energy when we come out. And for the hydrogen atom, we want solutions where V sub r is in fact of the form minus e squared over 4 pi epsilon naught r. So that when we look for solutions here, we're going to have a second derivative of u, a term that has 1 over r times u, a term that has 1 over r squared times u, and then that'll all equal a constant times u. Solutions to this equation are given by the Laguerre polynomials, associated Laguerre polynomials, so that when we write this again in terms of r, right, which again is u and l over r, we get a normalization factor, e to the minus rho over 2, rho to the l, and then these associated Laguerre polynomials given by certain numbers that depend on what L is. And that Laguerre polynomial is also a function of rho. And in this case, we always take rho is 2 over A naught times R. And A naught is the Bohr radius, h bar, over alpha mc. So again, we had, if we write out the lowest energy solutions for this, we're going to end up with something like R10 is 2 times 1 over A naught to the 3 halves, e to the minus r over A0, r to 1, 1 over square root of 3, 1 over 2A0 to the 3 halves, r over A naught, e to minus r over 2A naught, R20 is 2, 1 over 2A naught to the 3 halves, 1 minus r over 2A naught, e to the minus r over 2A naught. So we see for n, the maximum L is always 1 less than that. So L has to be less than n. And we could see that in the nomenclature for the associated Laguerre polynomial, where the subscript that we used was n minus L minus 1, and that number has to be greater than 0. And we also see, so they all have this exponential fall off with a scale A naught, the Bohr radius. As we go to higher orders, we're going to get a higher, a faster fall off. But then we also have this polynomial multiplying things. And finally, we need to note that the energies that we get out of this are minus E naught over n squared. And E naught is mc squared alpha squared over 2, or which is 13.6 eV, that you know. So that the energy levels start at a low energy, and then as n increases, they move up towards 0 from the bottom side, becoming higher and higher. Notice there's no L here, so all the L values have the same energy, and that ends up giving n squared degeneracy of energy levels. And that's not, some degeneracy is not surprising. We have spherical symmetry, and so since the m values are defined with respect to some z-axis, we expect that if we change that around to some other axis, it shouldn't matter, and therefore there should be a 2l plus 1 degeneracy due to the spherical symmetry, but the extra degeneracy to go from 2l plus 1 to n squared is due to an accidental degeneracy only with the Coulomb potential. So this is all true for the hydrogen atom, but for helium and lithium and all the other elements, it's not quite this simple, because the potential, the Coulomb potential, we need to modify. It's not just the nucleus providing an Ze squared over R term, but there's all the other electrons. And one can treat those as a cloud of electrons that shield the outer electrons from the full charge of the nucleus, and so that we have to modify with an average potential. However, we can still use this basis for talking about the various states that the electrons can be in. In particular, we're going to have the quantum numbers of n, L, and m to talk about the states that the electrons can be in any case, and but however, the extra electrons are going to break the n squared degeneracy, but not the 2l plus 1 degeneracy of any state. And before I go to the next page to talk about that, I will note that I've made a plot here, or used a plot, of the radial probability densities. These R values squared for the various states. So the 1s state, and they are multiplied by R squared as well, to take into account the volume. So the 1s state has this peak at a 0. It's where it's all mostly located. The 2p and the 2s, by the way, s means L equals 0, S equals L equals 0, P means L equals 1, D means L equals 2. So the two L possibilities for n equals 2, L equals 1, n equals 2, L equals 0 are shown by these two plots. So 1 is here, the 2p, and the 2s has this little peak, and then the bigger peak. That, by the way, the fact that there's this 0 in the 2s state comes from this polynomial having a 0. Now, the 2s state has more probability to be close to the axis than the 2p. This is even more apparent in the 3 states, where we have the 3s highlighted in red with its peaks, with the peak close, and 3 peaks. The 3p has a peak somewhere in the middle here, which we can't see, and then its main peak, and the 3d only has a peak well outside. So one could say that in the 3s state, the electron spends a little more time close to the center than it would otherwise. This will be useful for explaining the energy levels in atoms above above hydrogen. In particular, if we look at atoms that are somewhat like hydrogen, in this case, this is for lithium, and lithium, as you know, has a complete shell of S of 1, n equals 1. Complete shell. But the n equals 2 has only 1 electron in it, and so we can look at the energy levels of that state. And here's a compilation of them. So here's the ground state. You have one electron in this 2s state. It can be excited to a 2p state, which you see now has a higher energy, whereas we would have expected it to be the same energy, except for the fact that the 2s state spends more time close to, has a larger probability to be close to the nucleus, and therefore feel that attraction of negative energy pulling it down. So its average energy is lower. The first shell of electrons shield the electron in a 2p state from the full attractive potential of the nucleus, and therefore it doesn't have as low an energy. It's not pulled down as much. If we look at the 3 states, you'll see again we have this pattern that 3s is lower than 3p, which is lower than 3d, and the n equals 4 states and the n equals 5 states show this as well. So lithium isn't that interesting, but if we go to the next hydrogen-like one, in this case we have sodium has n equals 1 complete and n equals 2 complete. And then it has 1 in the 3 state, and so its lowest energy is in the S state. But the 3p state is higher, and 3d state is higher even than that. And then the interesting case is that because of the interaction of the S states with the potential, you can actually have this crossing where the 4s state is lower in energy than the 3d state. So as you're filling up electrons in this n equals 3, or the third row of the periodic table, we can fill up the 3s's and the 3p's, but the next thing we'll start to fill up is 4s before we go to the 3d. And this gives the peculiar shape of the periodic table where you have sodium and potassium, and then you have a big break and you go across. That first break on line 3 is, or on line 2 is not surprising. But on line 3, it's surprising that there's yet another line, but the next line after that, when we go to the 4th line, we don't fill up, we fill up 4s before the 3d. And then we fill up, and that is why that line is longer. The extra break is 10 long to fill up the all the possible d electrons. D is L equals 2, so there are 5 states, but we can put 2 electrons in each. And so with all that, we have explained the electron shells. So if I'll just go through that, right, so we have n equals 1 and L equals 0 possibilities, and then we have 2 electrons, and that's all we can have there. Then we can have n equals 1 and L equals 0. We can have 2 there, but we can also, in this case, have, this is n equals 2, L equals 0, and L equals 1. We can have 6 electrons there, and so these together make 8. So we have a shell of 2 and a shell of 10. And then we go to n equals 3, and we do L equals 0 and L equals 1 again. But the gap to L equals 2 is too big, so we just stop there, and we have the 8 here and the 18. But then we have n equals 4, L equals 0, L equals 1, and then we go back and fill in the L equals 2 from the n equals 3 state. And we have 10 plus 2 plus 6, which is 18, which then added to these gives the 36. Likewise, we sometimes talk about the state of the electron. For instance, for sodium, I'll go back to red here. For sodium, we talk about its electrons, and we say that it has a 1s state. It has 2 electrons in it, so we say 1s squared. It has 2s squared. It has 2p, 6, and then one final 3s. To give, that's the electron state of sodium, listing the states of all its electrons. Sometimes we just say it's 3s. We'll do something similar with nucleons. So that is the quick review of the hydrogen atom and hydrogen-like atoms and the shells of the in atomic physics and the structure of the periodic table. We'll want to do something similar with the nucleus.